Hello class, welcome to chemistry lecture. Today we want to talk about chemical equilibrium. I'm your lecturer Benjamin Ahinkra. Let's kick start. Well, the concept of equilibrium. When we say equilibrium, it's another term to represent or meaning equal. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. Rate over here means speed. So the reaction, the forward reaction and the backward reaction or reverse reaction occur or proceed at the same rate. So they will occur at the same time, at the same speed. Well, this is a brief illustration of the rate or chemical equilibrium. So as a system approaches equilibrium, both the forward and the reverse reactions are occurring at the same time. So this is the time axis. This is the rate or the speed axis. We have the reverse reaction represented by this curved line. Then the forward reaction represented by this blue line. So this is the forward reaction. So we have the substrate is N2O4 gas breaking down to produce two molecules of nitrite, all in the gaseous state. They are both in the gaseous state. You can see that these two graphs or these two curved lines overlap. So where they overlap, when you extrapolate it backward to the y-axis, the rate axis, we get a common rate. A common rate representing the rate for the forward reaction, common rate representing the rate for the reverse reaction, giving a rate. So like if we have 0 here and we have 100, then here will obviously be about 80 maybe meters, 80, the speed is 80 or the time it takes is 80. Then this is the time axis. Let's proceed. So as a system approaches equilibrium, both the forward and reverse reactions are occurring. At equilibrium, the forward and reverse reactions are proceeding at the same rate as previously described. So at equilibrium, you can see that the reverse reaction is here. The forward reaction is also here. They lie on top of each other at this particular time. So this dotted line represents equilibrium achieved. Rates are equal. Why is rate equal? Because they overlap over here. So when you extrapolate to the rate axis, you get equal rate for the forward reaction and equal rate for the reverse or backward reaction. And this is the same. This is the equation. N2O4 gas, the arrow pointing forward, produces two molecules of nitrate gas. Whereas two molecules of nitrate gas will, in the reverse reaction using the reverse arrow, will break down to produce N2O4. And this reaction is occurring at the same rate. Look at it. When you extrapolate backwards, you get the same rate. and this is the equilibrium. At this point in time, when you the two graphs overlaps to produce a common rate. Okay, once a system is achieved, once equilibrium is achieved, the amount of each reactant and product remains constant. This is the meaning. This is the reverse reaction, this is the forward reaction. At equilibrium, this is the dotted line representing equilibrium. So if this is 0 to maybe 200, then definitely this will be about 110, and this is not drawn to scale. So this is the equilibrium axis. So what we are saying is that once equilibrium is achieved, the amount of each reactant and product remains constant. So here they overlap at this point. The forward reaction and the reverse reaction overlap over here. So when you extrapolate to the concentration axis, this is the concentration axis. If you have from 0 to maybe 60, then the concentration axis, this one will be about 45 or 40. So it's equal concentration. So at equilibrium, what we are saying is that there is equal concentration of this product in the backward reaction and this product in the forward reaction. So when we say that a system is at equilibrium, what we mean is that rates become equal, that they have the same. When you extrapolate here, the rate becomes equal. The concentration to when you extrapolate from this, where they are overlapping to the y-axis, which is concentration axis, the rate, they have equal concentration, equal rate. In a system at equilibrium, both the forward and reverse reactions are running simultaneously, meaning that they are running at the same time. We write the chemical equation with a double arrow. I know this one you already know already. We write the chemical equation with a double arrow. This is the forward and this is the backward reaction. Forward, this is the substrate, this is the product for the forward reaction. Then the backward is this. This is the arrow representing backward. This is the substrate, this is the product. And this should all be in the gaseous state or the aqueous state or the solid state, but not, this one cannot be gaseous and this one being solid. They all have to be at the same state of matter. The equilibrium constants. Let's really pay attention over here. You can pause the video, the recording to study this at length. So pause the video and go through. Yes, now I know you are certain. So let's look at this reaction. We have N2O4 gas giving 2 molecules of nitrite. The forward reaction, as I explained, is N2O4 2NO2. You can see that we have removed the forward arrow alone. The reverse reaction is this. But for the reverse reaction, we reverse the position. We brought this one here and we brought this one there. So we have, in a nutshell, reversed this. We brought this one here and send this one there, and that is the reverse. So reverse, product becomes reactant, then the reactant becomes what? Product. The ratio of the rate constants is a constant as long as temperature is constant. Yes, before we can consider the rate constant, we have to keep temperature, which is T, at a constant value. The expression now becomes constant at equilibrium, K equilibrium, is equal to constant for the forward reaction over constant for the reverse reaction, all being equal to NO2 concentration, NO2 raised to the power 2, concentration, that's the bracket means concentration, this particular bracket, N2O4. To generalize the reaction, let's just simplify it. So this is the equilibrium constant, C, Kc. So these are the product, these are the reactants. So this is a general rule. You bring the concentration here for concentration of C, raise to the power whatever is in front of the C. We bring it, we raise it to the power. We bring the D, concentration of D. The whatever is in front of D, that's the oxidation, is it oxidation state or whatever? It's just showing molecules, number of molecules or number of atoms. We send it raised to the power. So we raise concentration of D also to the power what is in front of it. The same way we do the same for A. A raised to the power what the concentration in front of it. B raised to the power what is in front of it. This expression is true even if you don't know the elementary reaction mechanism. It applies to all reactions. Okay, so let's look at examples. Writing equilibrium constant expressions. Write the equilibrium expression for Kc for the following reactions. You may pause the recording and go through this question. Try to solve it on your own. Considering the forward reaction, the backward reaction. So just write out the equilibrium equation for it. So let's see. You can now unpause the video. You can now resume. Okay, so we are going to solve the questions. So A, 2 molecules of ozone, then 3 molecules of oxygen. They should all be in the same oxidation state. They should all be in the same state of matter, whether gaseous or aqueous or solid state or liquid state. The same, before you can compute the equilibrium constant. So for here, for the A, we have 3 raised to the power 0 oxygen, 2 atoms of oxygen. So the equilibrium constant is equal to O2 raised to the power whatever is in front of it. Then that's for the forward reaction or the product. Then we have what? The reactant. This is the reactant, 2 molecules of ozone. So ozone, that's O3 raised to the power whatever number is in front of it. So A is solved. We go to B. B is represented as 2 molecules of NOCl gas. So we have NOCl gas raised the concentration raised to the power what is in front of it, raised to the power 2, all over NOCl2. The NO has 2 in front of it, so NO concentration 2. The Cl2 has only 1 in front of it, and 1 is in front. 1 times anything is the same thing. So 1 Cl raised to the power 1 is the same. So Cl2 raised to the power 1 is the same. B is solved. Let's go to C. So C, for C2 we have we have silver ammonium So concentration bracket, there is nothing in front over here. It's only one that is in front. So silver and ammonium, silver and ammonia, forming ammonia salt, raised to the power 1, because 1 is what is here. We can't even see it. Then you multiply the product, the reactant, so silver and ammonia, but you can see that the silver has only 1 in front, so raised to the power 1, and is the same silver. Anything raised to the power 1 is the same thing. Then we have 2 in front of ammonia, so ammonia now becomes NH3 raised to the power what is in front, so 2. Let's carry on. So go and practice this. Write the equilibrium constant expression Kc for H2 gas plus iodide gas, forward reaction, backward reaction, 2 hydroiodide. Then we have Cd2 plus aqueous. So note the oxidation state. They should note the state of matter. They should be the same, gas, liquid, whatever, the same, before you can compute the equilibrium reaction. So here we have another reaction here. So let's go and see the solution. Okay, so for A we have Kc is equal to, this is the product, so Hi, 2 is in front, so Hi raised to the power 2. Then we have H2, then I2, we multiply them together, so we have this. This one, if we had different reactants, we would have multiplied them together. Okay, so let's look at the B. The B, we have CdBr4 raised to the power 2 minus. Since there is no number here and it's only 1, we leave it like that. So CdBr4 raised to the power 2 minus divided by Cd2 plus times 4Br. So Cd2 plus times 4Br times Br raised to the power 4, because there is 4 over here. Equilibrium can be reached from either direction. So we can reach equilibrium from the forward direction or from the reverse direction. The final ratio, looking at this reaction, the final ratio of NO2 raised to the power 2, that's this one, becomes NO2 raised to the power 2 to N2O4 reaches a constant to, and this is this one. So we have NO2 raised to the power 2 divided by N2O4 reaches a constant no matter what the initial concentrations of NO2 and N2O4 are, with constant time. So equilibrium constant now becomes NO2, we all know this already, NO2 raised to the power what is in front divided by N2O4. So this graph shows data from the last 2 trials from the table. So we have experiment 3 being the forward reaction, experiment 4 being the backward reaction. So this is what we were computing. It's already done. Okay, so still explaining why equilibrium can be reached at either direction. So we have nitrite, or we have 2 nitrogens, then 3 molecules of hydrogen gas. So nitrogen gas, anytime you see N2, nitrogen gas, hydrogen gas, then we have 3 molecules, then we have 2 molecules of ammonia gas. So they are all gas. Wow. So it does not matter whether we start with N2 and H2, or whether we start with ammonia, that's forward reaction, this is the reverse reaction. We will have the same proportions of all three substances at equilibrium. So meaning whether we start with this and this reactant to produce this product, or whether we start with 2 molecules of ammonia as our reactant to produce N2,3H2, what we are saying is that at equilibrium, whether we start with N2 and H2 or whether we start with NH3, we will have the same proportions of all three substances at equilibrium. We will have the same proportion of this, same proportion of this, same proportion of this at equilibrium. Okay, so what does the value of K mean? Yes, if K is far greater than 1, if K is far greater than 1, then the reaction is product favored. Products predominates at equilibrium. And if the reaction is reactants favored, reactant predominates at equilibrium. Let me explain this. Okay, this is good. So for the equilibrium constant, you can see this is the product for the forward reaction, this is the product for the backward reaction, but we are just looking at, let's just look at the forward. So this is the product, so we have NO2 raised to the power 2 as the forward reaction product. Then this is the reactant for the forward reaction, so divided by the reactant for the forward reaction. So assuming that this is 100 and this is 2, so 100 is what? NO2 concentration is 100 and N2O4 concentration is 2. So 100 divided by 2 will give us 50. So the equilibrium constant will be 50. Okay, let's take another one. What about if the top, the numerator NO2 is 10 and the denominator N2O4 is 5? We will get 10 over 5, which is equal to what? Which is equal to 2. So meaning that when the numerator, which is NO2, is big and the denominator is small, we will get what? K to be far greater than 1. What about if N2O4 is very big? Maybe we have 100 and NO2 raised to the power 2 will give us 2. So 2 divided by 100 is going to be 0.02. 0.02. Okay, what about if we have the down, the denominator N2O4, if we have N2O4 to be 4 and the numerator is also 4, then 4 over 4 will give us 1. Meaning that when the denominator is big, the numerator, the ratio we get will be very small, so the constant will be very small. But if the denominator is small and the numerator is big, then we can have an equilibrium constant to be far greater than 1. I guess you understand. Let's go. So that is the meaning of this. So the explanation, if the product is big and the reactant is very small, like I said, 100 over 2, we get 50, then K is far greater than 1. The equilibrium constant is far greater than 1. But if the reactant is big, product is small, so if the product is 5 and reactant is 10. Basically, we will get what? The constant to be less than 1. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. Let me take it again. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. So let's see. This is the forward reaction. This is the equilibrium constant. NO2 raised to the power what is in front. So NO2 raised to the power 2. Then N2O4. So it's divided by N2O4. We get 0.212. Even though we have not put in any numbers, we are just estimating or assuming 0.212. Okay, let's take the backward reaction. You can see the reverse reaction. You can see the reverse reaction. This one will be the reactant, this one will be the product. So we have 2N2O2 being the reactant over here. Then the product is for the forward reaction. So for the reverse reaction, this is the product. Forward reaction, this is the product. Reverse reaction, that's if you are moving from here to here using this arrow, then this is the product. So we have this. So the reverse reaction also gives us something like, it's supposed to give 0.212 divided by 1 over 0.212. That is the inverse, meaning that reciprocal is the same as inverse. Whenever you hear reciprocal, it's 1 over something. So if you want the reverse reaction of this is the reverse reaction of this one, then you just bring 1 over 0.212. This 1 over 0.212, which is equal to 4.72. You can even see that the reverse reaction is bigger than the forward reaction. The equilibrium constant for a net reaction made up of 2 or more steps can be found from the equilibrium constants for the individual steps. So if you have a big reaction, if you have a chemical reaction that combines 2 or more steps, then let's say we have 2 CO2 gas giving us 2 CO gas plus O2 gas. This is the first reaction, giving us equilibrium constant of 1.6 times 10 to the power minus 11. Then we have another reaction, 2H2O, giving us 2H2 plus O2 gas. Please, these ones are unbalanced, so don't worry yourself balancing them. So we have equilibrium constant K2 giving us an estimated figure of 1.3 times 10 to the power minus 10. When you put these two reactions together, these two chemical reactions together, then this is what we are going to get. We will get, when you put these equations together or chemical reactions together, you will get a single reaction, and this single reaction, the equilibrium constant of it is the equilibrium constant of the first one, K1 plus K2. So 1.6 times 10 to the power minus 11 plus 1.3 times 10 to the power minus 10 will give us K3. So you get K3 by adding K1 to K2. Equilibrium calculations. Let's look at Le Chatelet's principle. Le Chatelet's principle said that if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Systems shift from Q towards K. Well, so this is what it means. If a system at equilibrium is disturbed by a change in temperature, that if you heat the system, increase the temperature of the system, or you increase the pressure. Pressure can be you reducing the volume of the system, or increasing the temperature, whatever will increase the pressure, or the concentration of one or more component. That's if you add one or more of the reactant to it, the system will shift its equilibrium position so as to counteract the effect of the disturbances. So it's like buffer. If you add an acid to a buffer, the buffer will work to resist appreciable changes in pH. So this is working the same. The system will shift its equilibrium position so as to counteract or stop the effect of the disturbance, so that in the end there will still be what? Equilibrium. So let's see. If you add more of A, this is perfume particles. Perfume A, perfume B, when you add them together and you add more of A, the system, because you've added more of color A, the system will move from here to here. But if you add more of color A to this side, the system will move from here to here. Let's talk briefly about the Haber process. The transformation of nitrogen and hydrogen into ammonia is of tremendous significance in agriculture, where ammonia-based fertilizers are of utmost importance. So reproducing ammonia from 2 atoms of nitrogen and 6 atoms or 3 molecules of hydrogen, or from 3 hydrogen gases, will produce 2 molecules of ammonia, which is used in fertilizers. The Haber process. If hydrogen gas is added to the system, the nitrogen gas will be consumed and the 2 reagents will form more NH3. Yes, so if hydrogen gas, HH is hydrogen gas, HH is hydrogen gas, HH is hydrogen gas, NN is nitrogen gas. If more of this hydrogen gas is added, to the nitrogen, we form 2 molecules of ammonia. So the more hydrogen gas you add to the nitrogen, the reaction will be favored towards the forward reaction, producing 2 molecules of hydrogen gas, ammonia gas, producing 2 molecules of ammonia gas, as you can see. The Haber process. This apparatus helps push the equilibrium to the right by removing the ammonia from the system as a liquid. So we can see this equipment. If we have ammonia here, if you produce more of the ammonia, then the ammonia will give a negative feedback to the backward reaction that stop producing more of me, because I have enough. I am too much over here, so stop producing more of me. But if we remove the ammonia, if we produce and remove it, this side of the reaction, the reactant will see that there is more ammonia molecules needed, because we are producing but still it is being used up. Let's produce more, let's produce more, let's produce more. So that is the essence of the Haber process. Haber process says that this is the apparatus. This apparatus helps push the equilibrium to the right by removing the ammonia from the system as a liquid. So the more ammonia, to remove this ammonia, more ammonia will be produced. We've come to the end of the lecture. Thank you very much.